Hi there, and welcome to part 2 of the carbonyl functional group lesson. In the previous part A, you would have gone over aldehydes and ketones. Here we're going to jump to carboxylic acids, another derivative of it. So again, as a reminder, we're looking at molecules that have the carbon double bonded to an oxygen within the carbon chain somewhere. So a carboxylic acid in general will always be on the end, always, of a chain, and it looks like this. There's a carbon double bonded to oxygen with an OH group on it, and then the rest of the carbon chain somewhere. Don't forget that if we did the mirror image of this, where we've got the hydroxyl group on the other side, these would be the same molecule, just flipped. So this is called a carboxyl group, this functional group right here, the other one that we've been seeing a little bit more often now, so COOH. Generally, when it's written out like that in the name, we know that that's what's present. So for example, acetic acid you've been seeing for a long time is CH3COOH. A lot of times it's written as that to give you a clue to its structure. So it would be a carbon, carbon, just going based on this quickly so we can see a link between that. So that's how we would draw acetic acid. And that's why when you see these organic molecules with the carbons and then a bunch of things to the right of them, it's giving us a hint to its structure. So when we try to name carboxylic acids, we're going to replace the last letter, the E, with oic acid. So the example here is butanoic acid. I'm trying to use the butane chain throughout these lessons for consistency. If we had a butane chain that looked like this, with the oxygen double bonded on the end, that was butanal, that was an aldehyde. If we had the double bonded oxygen in the middle, that was butanone, the ketone. And then finally, butanoic acid, we have the same thing, a 4-carbon chain. On the end carbon, though, we've got the carboxyl group, which looks like this. So that becomes carbon 1, 2, 3, and 4. Okay, so to break it down, but means that there's a 4-carbon chain. An means that they are all carbon-carbon single bonds. And then oic acid tells us that there is the carboxyl group, which is on the end. So a lot of information in a simple name, and you notice that every few letters we're getting something new, and that's why we really need the exposure to continue practicing this. If we have something where there are 2 carboxyl groups on one of the ends, just for example, let's give ourselves an ethane here, keep it short. Okay, following along with all of the other examples we've done, we would call this a dioic acid. So 2 carbon chains would be F. They're single bonded, they have to be in this case. So they're ethane, and then dioic acid. There are trioic acids, that's what citric acid is. There are 3 carboxyl groups on that. So stay tuned and we'll look at those complex molecules later on. So carboxylic acids are weak acids. They lose hydrogens in solution, and that's how they raise the hydrogen ion concentration. And it is always the hydrogen bonded to the oxygen in this case. We do not lose these hydrogens here. They are not acidic, so they cannot be dissociated or ionized. But this hydrogen is acidic. And when we study later on in our unit, we'll learn more how we can determine that mathematically. So if we did a litmus paper test on this solution, our litmus red would stay red and blue litmus would turn red because it is acidic. Esters. So esters are a different type of functional group. This is the combination of an alcohol and a carboxylic acid. So in general, we've got a carbonyl bond, like we've been talking about, with an oxygen bonded to a carbon chain on both sides. So these always happen in larger, well, not really always larger molecules, but a little more complex. That first R group, we'll call R prime, that can be a hydrogen as well. It doesn't have to be a carbon group. But the carbon that has the double bond on it is considered the main chain, regardless of the length. Okay, so this carbon here, with that is the main chain. This portion here comes from the alcohol, so that has lower priority. Again, even if it's longer, it's going to be considered a chain because of the priority of the double bond that's there. So we know we're working with an ester when we see the OAT ending, and we're going to have to do a summary chart of this at the end, all of the different functional groups and how they affect the name of the molecule. So I've got methyl propanoate. So the parent chain comes from the furthest right. I've got prop, which is a 3-carbon chain. AN tells me they're all single bonded. O8 tells me that there's a double bond. Okay, this is the ester formation here to another, and I'll just kind of circle this here. This is what the OAT ending is telling me. And then there's another carbon on the other side of that oxygen, and in this case, it's the alkyl group methyl. So it's just 1 carbon. And then we'll go through and saturate. We'll do a condensed structural diagram here. If I wanted to see that as a line diagram, 1, 2, 3, it's going to be flipped upside down to the way I drew it. But we can see it just like that nonetheless. Now, if we'd want to flip that, we can name this propyl methanoate. Again, the length of the chain doesn't dictate what the parent chain is. It's where the carbon double bond. So this time, the carbon double bond is on 1 carbon because of the meth group. We've got that oxygen here for the O8 ending, and it's got to connect to a propyl group. So I'm trying to use all the different methods of drawing we've seen. There's going to be a hydrogen on that first one. So this is the methane portion. This is the propyl version. And these are 2 different molecules. They're not a mistake. Even though one is shorter than the other, the methyl can be the parent chain if it has the double bond on its carbon. Okay, so go back and rewatch that example if needed. That wraps this one up here. We can do one more example just to see how this is all related. We can do something such as ethyl butanoate. Okay, so if you want to pause and try that one. So if you have paused and tried that one, again, where to start with these molecules, start on the right side and scan backwards till you see the first prefix, which is but in this case. So 1, 2, 3, 4 as a line diagram. The carbon group has to be on the end with the oxygen double bond because it takes up 3 spots to make that. And then there will be an ethane group here. Structurally, if you'd prefer to see that, it's going to look like this. Now, if you did put that group on the first carbon, again, not an issue with that. We'll show these hydrogens as full structural here. And you can see the benefit of different types of diagrams as it gets larger. So if we had branching on this side of the molecule, that's not an issue. So let's add a couple of things to it. Let's put a chlorine group on this carbon here. And let's put a hydroxyl group here and a ether group here. So we'll put a bunch of different things. So we'll call this chloral hydroxy, and we'll put a methoxy group there. So let's say 2, 1, and this is going to be carbon number 1, don't forget, because that's got priority. So let's go 3 chloro, 4 hydroxyl, 2 methoxy, ethyl butanoate. All right, looks like we just threw a bunch of letters and numbers on a page, but we're going to make sense of that in a second. So we start on the right-hand side. We scan until we see our first prefix. Again, butane. So I'm going to want to say here, I'll do the structural one for this to start. 1, 2, 3, 4. Okay. The O8 ending tells me on one side of it, doesn't matter. I just like to go from left to right. We could easily put that OH and O group right here. So that's what the O8 group is. I'll just kind of box that off so you can see it. And then we build the molecule from here. We've got the parent chain down, so I'll now go back through and add it. I need to remember that that's carbon 1 because it's got priority. So carbon 2 has methoxy on it, which is oxygen bound to a methyl group. That's an ether. I'll name that below. Carbon 3 has a chlorine group on it. And carbon 4 has a hydroxyl group, which is an alcohol. So you can see how the name is an OL in this case, right? It's not butanol because the alcohol doesn't have priority. The ether does. And only one functional group can end the name. And in this case, it's the ester. This here is a halide. We'll add that in as well. And now that I've got everything in here, I've finished drawing it, I can add my hydrogens to saturate the carbon bonds and finish this off. For those of you that like the line diagrams, we've got 1, 2, 3, 4. And we forgot on this side, we forgot to put our ethyl group, which is a 2-carbon chain. Again, I want to stress the importance. This is not a carbon, the line that comes off of another atom. Okay, so there's 1 and 2 carbons in that case. So I've got that, I've got the chlorine, and I've got the OH. And it's not an issue drawing that up or down because this bond rotates, both are accurate. So there we go, putting a lot of pieces of information together. We could add double bonds to this, triple bonds, and it would still follow the same pattern. So we'll end off there on these short carboxylic acids and esters. Join us for part 3 where we look at compounds that contain nitrogen with this bond.